Okay, so our next speaker is Jens Lundell. He's a postdoc researcher in robotics at KTH in Stockholm, and he's working with Danica Krajic on robotics, perception, and learning. His research focuses particularly on data-driven approaches to robotic manipulation and grasping, and he has put a particular emphasis on in-hand manipulation with deformable objects. Jens completed his PhD in robotics at the Aalto University, where he addressed probabilistic multi-finger grasping in colored environments. And he also did his master's and bachelor's degree at that university in space science and technology. So one round of applause for Jens.
Hello. I'm gonna unmute you. Yeah. Hello. Thank you for being here. So I'm presenting today on behalf of Danica Krajic, who couldn't be here. And in comparison to the previous talk, I want to use less data. And but why we want to do this? Because we all seen the scaling laws, that everything seems to work much better just with compute, data set size, and parameters, at least for LLMs. I think the previous talk also confirmed that the same thing exists in robotics. We can really see that the test score error rate decreases with the size of the model and with the number of demonstrations. So am I just pursuing a goal that is ill-posed? Is there any reason to be like Scrooge McDuck? Initially, he was portrayed as this greedy person who had all the money in the world, but he didn't want to share it with anyone. And I don't think we should be like that, to use as little data as possible. But my thoughts are that we should be, at least we could be more careful with the data. We could use it more efficiently. And why would we like to do that? Well, this is a demonstration from our lab. So this is a AR teleop. The task was to stack blocks, right? Really small blocks. So you had to be really precise. And we use these MetaQuest controllers to do it. And this was very taxing. So after 10, 15 minutes, you just couldn't do this much more longer. And we also did the same for rice scooping. So getting 20 hours of data of this is kind of impractical. Although we have seen a lot of innovations in this as well, using these type of robotic manipulators, but not the embodiment of the robot to gather data. But still, I think we could do more with less data. And how can we do it? Well, in the lab I am in, we have used two things. One is equivariance, and I will talk about this today. So how can we use symmetry in data to do robotic tasks? We have specifically done it for grasping, which I will talk about. And another one is how can we use inductive biases? So how can we use physics-based information to learn better networks with less data? So let's start with equivariance. So what is it? I think a few of you maybe have seen it, but the mathematical definition is really this. It's a single line that contains a lot of information. So what it says is that if you apply some transformation to your data, g times x, so g is your transformation, you put that through a function, f. It should be the same as you first put your data through a function, and then you transform the data, so the output. It is more often showed in this diagram, so it just says the same thing. You can take any of these paths, going from x, applying the transformation, and then through a function, should equal that putting x to a function and then applying the transformation to the output. More practically, it's, let's say we have this cat and we want to segment it. It would look something like this. But then we could reflect it and it will look something like this. The thing is that we shouldn't have had to learn the segmentation again if we reflect it. We should just be able to reflect the output of it. And this is really what equivariance does. And it means that we don't have to see all transformations of the data. If we know some symmetry in it, we can just embed that into the network. or we could transform the data into a canonical space to learn these efficient models. And we took the same approach in one of our grasping work. So the idea here was, given an object point cloud, we wanted to constrain the approach direction here of it to be inside a cone. It's really that simple. And why did we want to do this? Well, one of our challenges was we wanted to grasp from a confined space, so from a shelf. And we didn't want to waste data on, but I do want to generate grasps from behind the object when we can't reach that with motion planning. So the problem is really like this. So we have the object, the grasp, and then we have the cone parameterized by an approach direction VA, and then an opening angle alpha. And we wanted the approach direction of the grasp, VG, to be inside of that cone. Mathematically, it looks like this. So we just wanted to learn the probability distribution of grasps and success condition on objects and the cone. This we can split into the following. So what this means is that we can want to learn the probability of success given a grasp, and then want to learn the probability of grasp given an object and the cone. Simply stated, we wanted to learn an evaluator and a sampler. And the neat thing here is that the evaluator don't have to care about the cone constraint, because the cone constraint is only useful for sampling grasps. This we learn with 2 different neural networks. And I will only talk about the sampler here. So what we first tried was just this simple variational autoencoder, where the input is the object, grasp, and the cone constraint. Then we condition on the object and the cone constraint in latent space, and we wanted to reconstruct the grasp. This should have worked, but it really didn't. Maybe we had too little data. So, but the nice thing here is that we have some symmetries in the data because of how we have the cones constraint. So this is the object in the camera space. So you can see the X, Y, and Z is the camera coordinate system. And what we can find here is that we can always transform or rotate this object to align with some of the axes of the camera coordinate system. So here we can find a unique rotation matrix that always rotate the blue object to be the approach constraint to be parallel to the negative y-axis. And why do we want to do this? Because then we can always generate grasp from only top down. And then because of the unique rotation matrix, we can transform it back into the original space. So in this way, we ensure SO2 equivariance. So our new sampler just looks like this. The thing here is also that because now we have all transformed the space into another space, is that we don't have to condition on the approach direction anymore, because the network knows that always have to learn grasp from top down. And this works very well. This is how it looks, the whole process. So we take the object and the cone, then we find the rotation matrix. We apply the rotation transformation to the approach space. We sample grasp there, and we do some evaluation and refinement of the grasp. We find the best one. Then we rotate back into the original space, and we can execute the grasp. The main thing that was that failed in this thing was not the grasping, it was actually the motion planning. So planning to these small confined spaces is not that easy. If you ever played with motion planning, you should know that. These are some other example of the same thing. So for instance, in the bottom right, we can see this blue picture, which we don't have a lot of wiggle room to grasp it. So this worked well. Compared to other networks, we get 10 to 20% higher grasp success rate. It's still far from great, but the thing is that the grasp kept is really like the number of sampled grasps is how many of those are within the cone constraint. And with our network, we are essentially up to 100%. So we really see that the network learned to adhere to this sort of soft constraint. Okay, so this was our work on. Yeah, and at CoRL, there are many works doing equivariance. So it's still a hot topic, and I think there's a lot of more work we can do there to be more data efficient. Okay, so that really concludes my part on equivariance. Let's move on to inductive biases. And what is inductive biases? Well, for one thing, equivariance is an inductive bias. It is something we know about the data that we can then use to learn better, and which could be good, for instance, for grasping. Another thing that we used an inductive bias is physics-based priors. So how can we use knowledge from physics to embed it into the network structure to really be able to, for instance, learn the dynamics model that could be used for predicting high-dimensional objects. So physics-based priors, one of them that we have used is the Lagrangian. So this odd equation really describes a lot of dynamical systems. It's made up of kinetic energy, the difference between kinetic energy and potential energy. And most of us knows that kinetic energy can be written as 1/2 times the mass times the velocity squared. This is just the same thing in matrix form. And where Q here, when Q dot means the joint positions and velocities. Another thing that nature has given us is the principle of least action. What this really means is that if I have 2 points in space, A and B, the nature will naturally have us to do the actions that leads to least. The trajectory from A to B should be the trajectory of least actions. It can be formalized in this differential equation. And then if we use this Lagrangian, we can solve for it, and we will get out this differential equation. Most of you have seen this. It's the manipulator equation. It's more commonly written like this. So it's an equation, the mass inertia matrix of your dynamical system times the joint acceleration plus the Coriolis and centrifugal force plus some gravity term. And we can actually use this to make networks, to embed them in the network learning. So let's say we have the same manipulation equation here, but we don't know the mass inertia matrix, which is very seldom known, and it requires a lot of engineering effort to learn it. And also, let's say we don't know the gravity term. What we can do is that we can learn these two with separate networks from data. So now let's say we only have a few samples of the joint position, velocity, acceleration, and the torques. What we can do then, we have this sort of network structure. So we put in the joint position into two separate networks, one to learn the gravity term, and another one to learn the mass inertia matrix to the Cholesky decomposition. What you can also do is that you can analytically derive the gradients of the partial derivatives of m with respect to q. And you can then use those analytical derivation inside your network, such that this would obey the manipulator equation. So with this, we can learn with just this simple loss function. So we learn to predict the torques. We also have to do a regularizer on the parameters because a Lagrangian is not unique. It's any Lagrangian that obeys this manipulate equation is a valid one. So that's why you need a regularizer. But one thing that Dellan overlooks is the geometry of the data. So it means that if you have two joint positions close to each other, it should mean that the predicted mass inertia matrix is the same or are very similar. This is not true. And what we then propose is that we want to enforce this geometric consistency while learning. So we want to have the mass inertia matrix to belong to the space of symmetric positive definite matrices. And we do this by a composition of three different networks. One is Euclidean network, so just a regular MLP. Then we use the exponential map to get it to the space of symmetric positive definite matrices. And then we apply some SPD layers there. So graphically, it looks like this. We have a Q in some space. Then we apply some MLP layers, which we then map to the cone. So this is the cone of symmetric positive definite matrices. And then inside of there, we apply a few more layers to get it to another feature space on that cone. So in this way, we ensure that the geometry holds. We also use Riemannian optimization to do all of this. And what we get out is that we can really see, like, just from a 2-3 data points, we are 10 times better than the Dylans. So this is really small data to learn a double pendulum, which is a very simple system. And this is also the drawback of this method. We can learn to predict how this 2-DOF pendulum works, but this is not really practical. We might want to learn the mass inertia matrix for humanoids or by manual settings. What we then did is that we introduced this reduced order Lagrangian neural network. So it looks rather simple. It's just an autoencoder that reduces the high dimensional space down to a low dimensional. And inside in the latent space, we learn a Lagrangian. Different from the previous work is that we use an ODE solver in the latent space to predict the next joint velocity and position. But the network is otherwise very similar to the previous one. We have 3 losses to enforce the Lagrangian dynamics and the reconstruction loss. And we again have to have the regularizing on the parameters. But it's a very simple system. And but one thing we also have to do, make sure, is that to learn these reduced models, we have to make sure that the pairwise layers of the encoder decoder are their inverses. So they should be multiplied together. They should be the identity matrix. And this is something we enforce while learning. And this is how the output looks like. So this is on a 16-DOF pendulum. And you can see that it works much better. We can actually predict. On the left, it's our best model, and we can really see how it follows the method, the pendulum. And this is really what we see also. If we don't do the reduced order, we have 10,000 times higher prediction error. So this looks nice. Can we scale it to more than 16 DOF? So that we did. We have more results in the paper, but this is our highest DOF example. This is 600 DOF plot, which we predict initially from the start. We predict the whole trajectory until the end using our learn model. You can see that it's a bit crumbled, but it's still, I'm surprised how well this actually worked. And yeah, this is where we are now. We would like to put this on a real system to learn from very few data points, the whole Lagrangian dynamics for that. And there are been at CoRL a lot of inductive biases papers. So it's still a hot topic, and maybe it's worth pursuing to do more with less. So these, before I wrap up, I want to thank my co-authors, Hao Fei and Sehang for CapGrasp, and Katarina and Noemi did the reduced order Lagrangian neural network. So I started off by showing the scaling laws, and it really seemed like that they do, it's just enough to scale. But I think it still pays off to be a little bit like Scrooge McDuck. I hope I showed a few examples that we can do more with less. Maybe we don't have to gather data for 20 hours. Maybe just 1 hour is enough, as long as we maybe have some equivariance and some inductive biases that we can embed. And yeah, this was it. I'm happy to take questions.
All right. Can you hear me? Do we have any questions in the audience?
It's such a good
It's
word.
I have one. So
Yeah.
We've seen many different approaches that have brought something to robotics. For example, diffusion policies have brought diffusion into the mix, and Now we're seeing flow matching models, etc. But all of them in the end sort of get merged into this transformer-like architecture for large-scale data learning. Do you see a way that you can include something like this also in these scalable architectures?
Yeah, so transformers are by nature permutation invariant, but the position embeddings actually breaks the equivariance. So it would be nice to see that. But one thing we see in CoRL was actually some work on how we can mask out the attention in the transformer to show like embed some inductive biases by that way. So if you have a kinematic structure, maybe your joints should just attend to your neighboring joints and all that. So that was a work on CoRL here doing that.
Yeah, there's one question.
One question about compute. Maybe you can give the audience an idea what kind of compute was necessary for the board.
Yeah. So the dynamical model was really just trained on a Mac. So this is she didn't have any graphics card, so we trained it on a Mac in an hour. So it's actually can do pretty damn cool stuff without much money. A Mac is expensive though, but you can use any other hardware.
All right. There's another question.
Just wondering, so you like shift this data efficiency with structure, physics, and variables.
Yeah.
I'm wondering if you have any comments on how to achieve this data efficiency from information theoretic perspective. For example, how to quantify the information on data and select so like for example so any comment.
Yeah, that's a good question. No, we haven't explored that yet. So it would be nice to see more work on that. I think it's a lot of theoretical groundwork that needs to be done to figure that thing out. One thing that you could do, like with the equivariance, is that you have to embed the symmetries. It would be nice if you can actually learn the symmetries from the data. If you know that the data might have some symmetries, could the network just learn it from itself? So instead of having to embed it. Okay.
All right. Then one last round of applause.
Thank you.